Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska, Fairbanks. Welcome to Unit 2, the Atmosphere, an Ocean of Gases. Today I want to highlight the fundamental ideas that we are exploring in this unit. To start, we see that the story of desert dust reminds us that the atmosphere and the Earth's surface are connected, and that weather systems can connect regions that are far apart around the world. Dust is transported across the Pacific from Asia to Alaska and made headline news in 2008. The dust scatters sunlight and creates spectacular red sunsets. In 2011, Alaskans were more concerned about the fact that this transport might carry fallout from the damaged nuclear reactors in Japan to Alaska. The key question of the unit is, what is the composition and structure of the atmosphere? The atmosphere is a mixture of gases. Minor gases can have important impacts. We investigate the atmosphere using the scientific method. Systematic observation and use of models is essential to understanding the atmosphere. The structure of the atmosphere varies with altitude, which we divide into 4 concentric layers, and the upper atmosphere is different from the lower atmosphere where we live. The composition of the atmosphere has varied since the formation of the Earth and continues to evolve today. The early variations were due to geological processes where gases were released into the atmosphere from the Earth. One of the great questions of our day is the rise in carbon dioxide. Carbon dioxide is a greenhouse gas that traps heat in the atmosphere. Our measurements of carbon dioxide show a long-term steady increase associated with burning of fossil fuels and a yearly variation due to seasonal changes in plant growth. Today's atmosphere is mainly made up of nitrogen, oxygen, and argon, where nitrogen and oxygen make up 99% of the atmosphere. Oxygen is unique as it both supports life and is created by living things. However, minor gases such as carbon dioxide, ozone, and water vapor play important roles in determining our environment. Water vapor is highly variable, and the humidity of the air can vary between 0 and 4% depending on the weather. Scientists use the scientific method to make discoveries and advance science. The scientific method is rational, even if scientists are not. The story of the ozone hole is one of the great detective stories in atmospheric science. When the hole was first discovered, many scientists thought it was an error in the measurements. The hole, shown by the pink area on the map over Antarctica, did not agree with existing understanding about ozone, which predicted high levels of ozone in polar regions, typical of the green areas shown on the map. Scientists made an educated guess that clouds in the Antarctic atmosphere were conspiring with industrial chlorofluorocarbons to destroy ozone. The educated guess or insight came from a group of scientists who had been immersed in studying the chemistry of ozone for a long time. This educated guess required new observations and new experiments so that its hypotheses could be tested rigorously. That testing required a major effort to make measurements in one of the most challenging environments on Earth, in Antarctica in the winter and early spring. While it took a while for other scientists to accept it, the evidence eventually stacked up in its favor and proved it to be right. Based on the science, international treaties were adopted to eliminate and replace industrial chlorofluorocarbons. The apples in the diagram of the scientific method reflect Isaac Newton's investigation of gravity that was famously prompted by his observation of apples falling from an apple tree. The famous tree is still alive in England and considered a national treasure. A scientific model is a tool for understanding. The Earth is big and we have only one version of it. We cannot turn elements of the atmosphere and Earth on and off to test ideas. We cannot decide to turn all rainfall off for a month and see what happens. Occasionally, there are events that do create experiments. After 9/11, commercial aircraft were grounded, and scientists used this period to see if cloud patterns changed due to the lack of aircraft contrails. However, scientists can use computer models to create virtual Earths, where they can do experiments and test their understanding of physical processes. The development of high-performance computers has been critical in advancing our understanding of weather and climate. The two maps show the distribution of radiosonde stations across North America and the distribution of surface stations in Alaska. As regards the radiosonde stations, look at how few stations there are in Alaska and northern Canada. As you look at these maps, think about the surface maps of weather systems we saw in Unit 1, and think about the size of a typical high or low pressure system. How many stations can give us a snapshot of a given high or low pressure system? The surface stations across Alaska are more common, and these are what provide us with our reference for the observations you will make in your community this semester. As you make your measurements locally, I hope you feel you're adding to the network of surface observations across Alaska. The temperature of the atmosphere varies with height, and we divide the atmosphere into layers based on those variations. The ground tends to be warmest, though not always, during an inversion in the Alaska winter. The atmosphere then cools with height in the troposphere up to the tropopause. Then the atmosphere warms in the stratosphere up to the stratopause. This heating is due to the absorption of sunlight in the ozone layer in the stratosphere. Above the ozone layer, the atmosphere cools again in the mesosphere up to the mesopause. The mesopause, near 80 kilometers or 50 miles high, marks the top of the well-mixed nitrogen-oxygen atmosphere. In the thermosphere, the atmosphere warms again and the composition changes due to energy from particles from the sun impacting the atmosphere. The aurora reminds us that the upper atmosphere has unique characteristics and plays host to unique processes. The sun emits both light and heat, but also a stream of particles called the solar wind. Atoms and molecules in the upper atmosphere are ionized by both the radiation and collisions with the particles of the solar wind. The ionosphere is so called because of the high levels of ionization in this region. Ionized particles in the atmosphere interact with radio waves and can disrupt communications. The aurora is created through a complex and complicated set of interactions between the solar wind and the atmosphere and the Earth's magnetic field. As a result, energetic particles are accelerated into the atmosphere and collide with atoms and molecules, giving them energy. The atoms and molecules then release their energy by emitting light and fluorescing, which is the aurora that we see. The bottom layers of the aurora are at about 50 miles high, just above the mesopause. During solar storms, the solar wind is stronger and results in spectacular auroras and also disruptions to communications and navigation satellites. Alaska encompasses several climate regions because of its vast size, high latitude location, proximity to oceans, and complex topography. We can identify 9 distinct climate regions in Alaska, from the Arctic with a polar tundra climate to the southeast panhandle with a moist maritime climate. The climate in each region is determined by a variety of geographic factors: latitude, distance from the ocean, altitude, and presence of mountains. We will see all these factors in play as we explore our weather observations from across Alaska this semester. Can you identify your climate region in the map on this slide? We can readily see these effects in measurements from different stations across Alaska. The temperatures in Fairbanks and Nome, shown in the upper right, highlight the moderating effect of the ocean. Nome and Fairbanks are essentially at the same latitude, but Nome lies on the coast and Fairbanks lies 400 miles or 640 kilometers inland. Both communities have the same annual temperature, but very different weather and climate. Nome has a more moderate maritime climate with warmer winters and cooler summers. Fairbanks has a more severe climate with colder winters and warmer summers. The difference in precipitation in Golconda and Valdez is shown in the lower right and highlights the effects of mountain ranges on precipitation and climate. Golconda sits about 80 miles, 130 kilometers north of Valdez. Warm, moist air, traveling north from the Gulf of Alaska, rises over the Chugach Mountains. This results in precipitation on the south side of the Chugach Mountains and contributes to the 285 inches, 7.3 meters, of annual snowfall in Valdez. The now drier air continues on to Golconda and contributes to a much lower 57 inches, 1.4 meters, of annual snowfall in Golconda. Golconda sits in the rain shadow of the Chugach Mountains. This coastal snowfall also maintains the large glaciers in southern Alaska and shows how mountain ranges can radically influence weather and climate. We can also see the difference in Alaskan climate regions by comparing the temperature and precipitation in the interior and Copper Valley with that in the Southwest Islands. In the interior, we see a seasonal temperature range of nearly 90 degrees Fahrenheit, or 56 degrees Celsius, between the summer high temperature in July and the winter low temperature in January. In the Southwest Islands, we see a much smaller seasonal temperature range of about 30 degrees Fahrenheit, or 17 degrees Celsius. We see that the Temperature ranges in each month are also larger in the interior, about 20 degrees Fahrenheit or 11 degrees Celsius, than in the Southwest Islands, where they are about 10 degrees Fahrenheit or 6 degrees Celsius. This difference again highlights the moderating effects of water and humidity seen in maritime climates. Both the thermal inertia of water and the greenhouse effect of clouds and water vapor contribute to the smaller changes in temperature over seasons, months, and days in maritime climates than in continental climates. Final thoughts and summary. The atmosphere is a thin envelope of gas that defines the environment of the Earth's surface. The atmosphere, Earth, and ocean are linked. The atmosphere of the Earth is constantly evolving through natural and human processes. Atmospheric gases that are found in small amounts can be very important. Our weather occurs in the troposphere. The scientific method provides a systematic framework for discovery. An observation network is essential for understanding the atmosphere. Atmospheric models are also essential for understanding the atmosphere, and getting our observations and models to work well together is a major challenge in atmospheric science. The upper atmosphere, unlike the lower atmosphere, is dominated by charged particles and responds to electrical and magnetic processes. Alaska's vast size, high latitude location, proximity to oceans, and complex topography provides a natural laboratory for studying weather and climate. In closing, the importance of the atmosphere can be summed up by the view of the Earth from the Moon. The Earth's atmosphere is in a balance with the planet and maintains life on our planet. It is a complex system that can be full of surprises. It's a major challenge to understand the weather and climate and requires a systematic approach in both observations and modeling. Thank you.